Welcome to the next video in the Discrete Math video series. And so this is video 11, in which I'm going to solve the problems that we set out last time. And so down here, translate the following into a symbolic expression. Now, the way that I handle the word unless is that effectively that's just a disjunction. So unless is effectively the same thing as or. So this could be expressed as you cannot edit, right? So that is the negation of you can edit the Wikipedia page, a protected Wikipedia page, or you are an administrator. So that's that, pretty straightforward. Let's move on to problem number 2. You can see the movie only if, right? So that looks like a simple sentence before the word or the phrase only if. So that makes it seem like, and I'm going to use S. I don't know if that's the letter that the book uses, but I'm going to use S for you can see the movie. And so only if means an arrow going in that direction. You are 18 or older, so I'm going to say E for 18 or older, and then, or 18 or whatever that says. Or, so that's the or right there. You have permission of a parent, so that would, I'm just going to say P for permission. And this is the inclusive disjunction. I think that makes just very good sense because intuitively you should still be able to see the or if you can see the movie, then one or both of these things is true. I think it's fine if both are true. Maybe a little comical, but still logically correct. So okay, let's move on to the third thing, and this is going to involve a whole bunch of symbolizing. So I'm going to go ahead and be a little bit more careful about just being explicit about what symbols I'm using for which propositions. So I'll say that the system is in the multi-user state is represented by S, and then I'll say that it's operating normally. That is represented by N. Again, I don't know if this is what the book is using, so I mean, it should be pretty straightforward to use whatever the book requires you to use or whatever. So anyway. If it is operating normally, so that's something we've already labeled, the kernel is functioning. So I'll label that with K for kernel. And then the kernel is not functioning, or the system is in interrupt mode. So I'll use I for interrupt. And then the system is not in multi-user state. Actually, maybe I should go back. I might just remember this a little bit better if I label it M's for multi-user state. So, okay, and the system is not in multi-user state, then is in interrupt state. The system is not in interrupt mode. Okay, cool. So let's now, with this kind of key for what symbols correspond to which sentences, we could say M if and only if, so I'll use this biconditional, M if and only if it is operating normally. So that's one sentence. If it is operating normally, the kernel is functioning. So if N, then K. The kernel is not functioning, so that would be not kernel, right? Kernel is not functioning. Or the system is in interrupt mode. And here I'm going to use the inclusive disjunction. Does that seem correct? Could it be not simultaneously not functioning and in interrupt mode? I think it could, right? Unless there's some particularly strong reason to think that this should be exclusive, then I'm not going to use the exclusive disjunction. Okay, and then if the system is not in the multi-user state, so that's like if not multi-user, then it is in the interrupt state. So that would be this right here. And then finally, the system is not in the interrupt mode. So not I. Okay, cool. So with all of these sentences together, we need to basically decide, is it possible to assign each one of them the value true? Right? So I would like, basically that's what we're asking when we're asking whether the specification is consistent, is that, if you tried to make all of these simultaneously true, could you? Is there any way of assigning truth values to the components such that all of these come out true. Okay, well, let's try to work like this. If this is true, then the value of I must be, how do I want to represent the value? I'm going to maybe say like the value of I would be false, right? So in order to make the negation of I true, you would have to make the value associated with I to be the false value. Now let's see how that, so to speak, ramifies through the rest of the sentences. So if I is false, and we have an I here, and we're trying to make all of these sentences true, well, keep in mind that a conditional is true in just about every case, but the one case it's not true in, right, so this will not be true in the case where you have basically if true then false, right? Like this is basically the one situation that evaluates to false. And since I, we now know, is false, then we are in danger of having this scenario, right? Like in having this kind of a case, unless we do something to ensure that the antecedent takes the value true. So we need the value of negation M should not be true, right? As long as we make the negation, right? Like as long as we make the antecedent not true, then that will entail that the entire sentence comes out true, right? Because, you know, even if you have false, false, this evaluates to true. And if that is at all confusing, go back to the lessons discussing the conditional and, look at the truth table for the conditional and so on. This often confuses people. So if this confuses you at all, go make sure that you understand the truth table for the conditional. But this is, right, so if we could make the antecedent false, then this would all work out. So let's try to do that as best we can. Well, okay, but there's really just one thing to do, right? So since we need, so we need the value of negation M to be false. So that means we need the value of M to be true. So we've decided M is now true. Okay, now let's keep going. Again, here, we know the value of I. We've already decided that I is false. Well, again, right, if we're trying to make the entire sentence here come out true, and the right-hand disjunct is false, then we had better make the entire left-hand disjunct true. So we need that the value of negation K is true. Therefore, we must have that the value of K is false. So we've now decided that K is false. Now, let's come up here. We've now decided that this K, right, that's the same K, is now false. And by the same sort of reasoning that we used down here for this conditional, we now have to do it again and say that in order to make this proposition true, we need the antecedent, in this case N, we need N to take the value false in order to make the conditional true. And then now we have that this N here is false, right? We've basically decided that already. This M, we've also already made a decision about. We decided over here that it is true. And we were kind of forced to do that. I mean, like, you know, right? We don't really have much choice about what to assign I. That's where all of this got started. And so if we're going to make, you know, this sentence true, like this has to be the assignment. There aren't really options here. And then from that, we were sort of forced to say that the value of M is true. Like that's, again, kind of non-negotiable based on everything that we have here. So, so we have to say that I is false. We have to say that M is true. And similarly, K has to be false. n has to be false. Well, by the time we've done that, we've now found that this entire sentence takes the values true and false on a biconditional. Well, that means that this biconditional is now false. And because the biconditional just has to take the value false based on everything else that we've reasoned through so far, then that means it is just not possible. It is just not possible to make all of these sentences true, right? Because by the time we reach the end, we have now been forced to make assignments of truth values to the components so that this one is false. So like we just didn't, right, there was no way to make it work. And so what that means for the question is, is it consistent? No, this specification is not consistent.